Good morning. I would start the class now by sharing my screen. Um, so I want to welcome you once again to Chemistry 121, Introductory Chemistry 2. Today we'll be looking at gases. Particularly, we'll be looking at the kinetic theory of gases. We'll look at gas laws. We'll look at equations that are used in treating gas laws and the like. Once again, my name is Dr. Felicia Gumede. I'm teaching with Dr. Oluseyi and Professor Istanbul. When we talk about, or anytime we want to look at gas or gases, we'll first look at the uniqueness of the gas phase. You know that there are three states of matter, actually four, but we are looking at the third state of matter, which is the gaseous state. You can have solid, liquid, gas, and plasma. We are looking at gases, and because of the very distant nature of the particles of gases, demonstrate physical properties that are nearly independent of their chemical identity. So gas behaviors are remarkably different from that of solid or liquid. And this is as a result of a far distance between the particles that makes up gaseous phase. They have lower density than liquid. They are easily compressed than any other state of matter. The compression is as a result of the closing up of the distances that are within their particle sizes. So when you apply pressure, the distance that exists between the particles is reduced, and as a result of that, you have its compression. Because of the fact that they are distant from each other, gases assume the volume and the shape of the container in which they occupy, and they can mix evenly because of the random motion of their particles, and they can diffuse and occupy the confinement in the container they occupy. As a result of all this, there is the effect of pressure on gases, which is not that so common on solid and liquid. Pressure significantly affects gas behaviors, as again its effect on liquid and solid, because liquid and solid are considered to be incompressible, non-compressible, while gases are compressible matter. So when you apply pressure, you are talking about the application of force over a region of space. So force over area. Pressure is expressed as force over area. So pressure is equal to force exerted over a specific area. Now, when you apply the force, it reduces the space between particles, and you have that effect, that compression effect on your material. To understand what we are talking about, we can use the atmospheric pressure. As a result of the volume of air in the atmosphere, there is the pressure exerted on the earth by that volume of air. So you have at the sea level, the atmospheric pressure is 1 atmosphere. When you move 4 miles into the atmosphere, then you have 0.5 atmosphere as the pressure. And as you move further into 10 miles into the atmosphere, you have 0.2 atmosphere as the pressure. Meaning that as you move away from the surface of the earth, from the sea level, you have a reduction in the pressure associated with volume of air that is existing within that region. Now, atmosphere is one of the units of measuring pressure, but it's not the only unit that you can use to measure pressure. You can also measure pressure in millimeters of mercury. So pressure is simply the weight of the Earth's atmosphere pulled down by gravity. So if you have mercury and you put a glass tube, mercury in a bowl, and you put a glass tube, there will be a rising of that mercury as a result of atmospheric pressure. And the distance that that mercury would move is 760 millimeters. So one atmosphere then translates to 750 millimeters of mercury. You can use a barometer to measure atmospheric pressure on a daily basis. However, in the laboratory, a manometer is used to measure atmospheric pressure. The manometer is designed in such a way that you have a movement of your mercury. When the manometer is closed, you have the mercury level balanced off. The mercury level is equal to each other. But by the time you open it and you introduce pressure. By the time you open it and you introduce pressure, the mercury will move and there will be a change in the height. That change in the height can be used as a measure of your pressure. The change in this height from what you initially have to what you have newly can be used as the measurement of your pressure. So if you have, for instance, your manometer that has not been opened, if you have the pressure of the gas will be equal to the pressure of the atmosphere. Now, when you then have the pressure of the gas lower than the pressure of the atmosphere, then you can be able to, you have this situation. The pressure of the atmosphere would move the mercury by a distance of delta H because you have a lower, so the atmospheric pressure is greater than the pressure that is coming from the gas. At the other end, if you have the pressure that is coming from the gas greater than the pressure that is coming from the atmosphere, then the pressure of the gas will move the mercury by a distance of delta H. Then you have your pressure of the gas will be equal to pressure of the atmosphere plus delta H as against pressure of the gas because the pressure of atmosphere minus delta H that you have at lower gas pressure compared to the atmosphere. So you use that to measure atmospheric, you measure the pressure of the gas. Now, like I mentioned previously, the unit for measuring pressure can be millimeters of mercury, the distance that the mercury moved when you introduce pressure. This unit is also the same as torr. Torr is another unit of measuring pressure, and one torr is equal to 1 millimeters of mercury. So when you have 760 millimeters of mercury, it means it's also the same thing as 760 torr. There is another measurement, unit for measurement of pressure that is a derived SI unit. Derived in the sense that you have SI units that you converted into the derived form. You know that we can measure force as Newton, and we measure area as meter squared. And we have mentioned that pressure is force over area. So in that case, pressure will become Newton per meter squared. Force being Newton, area being meter squared. So you can also express pressure in Newton per meter squared, which is also known as Pascal. So 1 Newton per meter squared is the same thing as 1 Pascal. At standard condition, STP, standard temperature and pressure, 1 atmosphere at 0 degrees Celsius, which is 273.15 Kelvin, would be equal to 760 millimeters of mercury. It will be equal to 760 torr, and it will be equal to 101.325 kilopascal, which can also be expressed as 1.01 times 10 raised to power 5 Pascal. And you know that Pascal is the same thing as Newton, Newton per meter squared. So you have 1,000 Pascal to be equal to 1 kilopascal. Don't forget that at STP, 1 mole of gas will occupy 2.4 liter or 2.5 GM3 volume. And at STP, you have 1 atmosphere and 273.15 Kelvin, which is 0 degrees Celsius. All these are very important because we are going to use it when we get to calculation. Now, for us to be able to fully understand how gases behave and why they behave the way they behave, we are going to look at the kinetic molecular theory postulate. What are the postulates of kinetic theory? What does kinetic theory state, and how will it then affect what you have about the properties of gases? The number 1 postulate is that gas consists of large number of particles. They consist of large number of particles. It could be atoms, for gases that are monoatomic, like helium, like neon, those ones that are noble gases, or it could be molecules for gases that are di or tri or whatever number of atoms. You have O2, oxygen, N2, nitrogen, O3, ozone, and the like. Those are molecules. They contain, so gases contain large number of particles. These particles are separated by large distance compared to the diameter of the container. Compared to the diameter of the container, compared to their own particle diameter, in such a way that it is assumed that their own diameter, their own size is negligible. So the first assumption or the first postulate is that you have a large number of particles, you have a large number of particles in gases, but their sizes are so small that the particles are negligible in size. Then the volume of each particle is so small that it is assumed that they have masses, but they have negligible volume. So that's the number 1 postulate, the number 1 assumption in kinetic theory of gases. The sizes are negligible. Large number of particles, they have masses, but their sizes are negligible. The number 2 postulate is that the gas molecules exert neither attractive or repulsive forces. So which means that we are saying that the particle does not have effect on each other. There is no interaction between them. Because the distance between them is so far, the force that can exist between them will transverse a very large distance, and it is assumed that they are not attractive nor repulsive to one another. So no force between the particles except when they collude. It's only when there is collusion between them. There is no attractive force, there is no repulsive force. So that's the second postulate, the second assumption of kinetic theory. The third one is that particles are gas particles are in constant, rapid, straight line motion in random direction. What this means is that the particles are diffused. The particles are moving. They are constantly moving. They are moving rapidly. They are moving in a straight line. And the direction of the movement is not regular, it's random. Then the number 4 postulate is that when the gases collide, don't forget that in postulate number 2, we mentioned the fact that because of the random motion, they collide with each other. So when the particles collide with each other and they collide with the walls of the container in which they occupy, the collision is elastic, perfectly elastic. The implication of that is that there is no kinetic energy transfer. When an object generally collides with another object, there is expected to be a reduction in the kinetic energy when it bounces back because of the loss of part of its energy to the object or to the other particle it collides with. So by the time it's bouncing back, there should be a loss of some quantity of kinetic energy. But the assumption in kinetic theory is that that is not occurring when particles collide with each other, when gaseous particles collide with each other or with the wall. So that means that the kinetic energy after bouncing back is the same with the kinetic energy with which they eat each other or eat the wall. So what that connotes to us is that they are randomly moving, they collide with each other, and that collision is perfectly elastic. They go back in the straight line, maintaining the same kinetic energy. The kinetic energy is conserved. Now, the last one of the theory is that the average kinetic energy, when you have all the particles put together and you look at each of their kinetic energy and you find the average kinetic energy, that average kinetic energy is directly proportional with, the Kelvin temperature of the gases. So this is one of the ways to actually define temperature. So you can define temperature as the average kinetic energy of the particles in the body. Now, the implication is this: when you increase temperature, you increase average kinetic energy. Particles start to move at higher kinetic energy. When you reduce temperature, you reduce the kinetic energy. Particles start to move in slower rate. So what this implies is that temperature and kinetic energy and the average kinetic energy of the particles, all the particles put together, are directly proportional. So any two gases with the same temperature will therefore have the same kinetic energy, average kinetic energy. So when you have oxygen molecule and argon molecule, and the two of them are at the same temperature, they will have the same average kinetic energy. By the time we start to look at the gas laws or the laws that guide interaction in gases, we'll be able to use some of these postulates to explain what we're talking about. So for us to understand what we have learned, let's look at typical examples of situations that we are talking about. So imagine to have a sample of gas, and you have that sample of gas within a container, and you have closed the container. What the theory is trying to say is that the particles of the gases are in constant motion. So there is a chaos. And because of that constant motion, they will bump into each other constantly. So you have this collision here. Then they will bump into the wall. So you have the collision against the wall. You have the collision against each other. So two types of collision: collision against the wall of the container, collision against each other. So as you have that collision, the assumption is that the collision is perfectly elastic. So two molecules may stop completely until another collude with each other. So if you don't have, if the there is a loss of energy by the collision, it will get to a point that they will not be able to move again because they are losing energy as they collide with each other. So the assumption is that as long as they continue to move, it means that there is no loss of energy in the course of their collision. So the velocity with which they are moving is maintained. And that helps us to come up with the concept of the average kinetic energy, which means that you have some of the molecules moving fast, some of the molecules moving slowly, but when you put them together, the average kinetic energy becomes constant. So this is also to illustrate what we're talking about. Now, if you look at 273 Kelvin, which is 0 degrees Celsius, you have this to be the kinetic energy, I mean the velocity with which your gases are moving. You have different distribution of the movement of the speed, but the average is what we have here, and that average is directly proportional to the temperature. You will see that as you change the temperature, the average kinetic energy is changing. You have an addition of 1000 Kelvin, and you have the average kinetic energy changed. The average kinetic energy increased. You have a lower average kinetic energy at 273. You have an increase in the average kinetic energy at 1273. So which is that's the average kinetic energy here. Then you have another increase in the average kinetic energy at 2273. So as you increase the average kinetic energy, as you increase the temperature, you increase the average kinetic energy. So any two gases at same temperature will have the same average kinetic energy. We talked about that previously. So how does gas law then work? Or why do some gas law work so well? Because of the assumption that we have, the kinetic theory, the assumption of the kinetic theory supports the principle behind gas law. So recall that gas law applies to any gas. The chemical identity is not important. Gas particles only interact when they collide. Since the interaction is so short, the chemical property does not, don't have time to take effect. So because there are no chemical reactions involved, there is no chemical change, the collision does not lead to chemical interaction. It helps gases to work, the gas law to work. So let's start with the first one of the gas law that we want to look at, and that is the Boyle's law. Boyle's law simply tells us that the volume of an average of a fixed mass of gas is is inversely proportional to the pressure. So volume is inversely proportional to the pressure, or pressure is inversely proportional to volume. So which gives us the expression P is inversely proportional to 1 over V, and it means that pressure will be equal to K constant over V. So which means that PV will then be constant. So that is the equation for expression of Boyle's law. Now, for us to be able to understand it, we have data that actually speak to that. Now, what does the data tell us? If you look at the volume here, as you change the volume, as we reduce the volume, you would notice that the pressure is increasing. The change in pressure is increasing. You have your manometer, you are introducing, you have 1 atmosphere, and this is what you have. Your change in H is expressed as that. As you pour in more pressure, your change in H would change. So as you increase pressure, the volume, you would also notice that you have, this is your volume of the trapped air, but your volume is reduced. So as you increase, as you increase volume, you reduce pressure. As you reduce volume, you increase pressure. And it becomes directly proportional over P, inversely proportional to P. So a plot of volume against temperature will give you a negative slope showing inverse proportionality, but a plot of volume against 1 over pressure will give you a positive slope because it is directly proportional as 1 over P, but inversely proportional to pressure. So you can then express, your the Boyle's law as P1 V1 is equal to P2 V2 because PV is constant. To be able to illustrate what we are talking about, if you have a container that has gases in it and you are putting a load of 1 kilogram, the pressure that will be exerted is force over area. The pressure that will be exerted at 1 atmosphere would give you a volume that is L, 1 liter. But when you decide to reduce that, if you decide to increase the load, force over area will increase because the area is constant, but the mass that you are bringing in, the force that you are bringing in, which is mg, is higher. As a result of that, you will see that the pressure will reduce the volume to 0.5. So you have, and what is responsible for that is that there is a close in the space between the particles. The distance between the particles have been reduced, then there is a close in the space. That is in line with postulate 1 and 2, that there are far distance and no interaction between the particles. The second law is the Charles law. Charles law tells us that volume is directly proportional to absolute temperature. So the volume of a fixed mass of gas is directly proportional to the absolute temperature. So in this case, V is equal to Kc. V is equal to constant times C. So then if you make constant the subject of formula, then V over T will be equal to constant. And if V over T is equal to constant, you can mathematically express Charles' law to be V1 over T1 is equal to V2 over T2. Don't forget, your temperature must be absolute temperature. So if you have highs, and you have a tube, you have a gas inside the tube, you maintain pressure. Don't forget that these laws, in expressing these laws, your For instance, in Boyle's law, your temperature must be held constant. In Charles' law, your pressure must be held constant. So if you have a constant pressure, you are not changing the pressure, and you put your gas inside high, you will have you have this volume, the volume maintained here. But by the time you boil, you heat to 100 degrees Celsius, which is 273 Kelvin, you have an expansion of your particles. Then your volume will increase because of theory 2, theory 5, that says the average kinetic energy will increase when you increase temperature. Because the average kinetic energy increases when you increase temperature, there will be an expansion, there will be faster movement, faster collision, and there will be expansion of your volume. Now, this expression is a plot of volume against absolute temperature. When you plot volume against absolute temperature, then you will have a linear interaction. And that linear interaction is dependent on constant pressure. But if you change the number of moles, it will still be linear, but your slope will be different. That is what we're going to discuss next. Now, the principle is that you have your low kinetic energy at low temperature, and because you are at low temperature, the low kinetic energy would make the volume to be to be small, to be lower. But when you increase the volume, and when you increase the temperature, there will be increase in average kinetic energy. And when there is increase in average kinetic energy, there will be increase in frequency of collision with the wall, and as a result of that, there will be expansion in the volume. There will be increase in the distance between particles to each other. You will see how kinetic theory explains all these laws. So the same thing here. You have your at low temperature, you have lower volume of your gas. But when you increase temperature, there will be an increase in the frequency of collision with the walls and with this mercury block that is representing your pressure, that is held constant. And as a result of that, there will be an expansion in the volume. Now, this is an expression for us to try our hands on. We want to use gas law, particularly Boyle's law, to determine an unknown. You are given a sample of carbon monoxide that occupies a volume of 3.2 liter. So this will be our V1 at 125 degrees Celsius. This is our temperature. We'll convert it to Kelvin, which must be plus 273.15 Kelvin. So as a result of that, you have 398.15 Kelvin. Then at what temperature will the gas occupy a volume of 1.54? So you have the new volume to be 1.54, and our temperature 2 is the unknown. So we can make T2 the subject of formula here, and we'll have V2 times T1 over V1. So you have, then you substitute for your variables. You have V2, you have V1, and you have T1. During the dimension analysis, you have volume cancel volume. As a result of, at the end of the day, you have 192 Kelvin to be your answer. That is the demonstration of what you have in Charles' law. Now, the next law is the Avogadro's law. What Avogadro's law says is that equal volume of all gases contain the same number of molecules at STP. So what that means is that volume is directly proportional to number of moles. So equal volume of gases contains the same number of molecules at STP. So when you maintain temperature, you maintain volume constant, you will have volume to be directly proportional to number of moles. And mathematically, V is directly proportional to N. So V is equal to constant N. That means that if you make constant the subject of formula, then you have V over N is equal to constant. So we have V1 over N1 is equal to V2 over N2. So you have a plot of volume against number of moles, and you will have a positive slope direct relationship. So as you increase the number of moles, you will increase the volume. As you reduce the number of moles, you will reduce the volume. So if you have ammonia bonds in oxygen to give you nitric oxide and water vapor. So that's the equation of reaction. I mean, how many volume of nitrogen oxide or nitric oxide are obtained from 1 volume of ammonia at STP? Now, what you will just need to write is write a balanced equation of the reaction, and you will now be able to say that every 4 mole of nitrogen, no, of ammonia, produces 4 mole of nitric oxide. So that means 1 mole of ammonia will produce 1 mole of nitric oxide. And at STP, Avogadro's law says that equal volume of 4 gases will contain the same number of moles. So which means that number of moles is equal to volume. So we can translate number of moles to be equal to the volume. So 1 volume of ammonia will, as a result of that, produce 1 volume of nitric oxide. Now, what is the principle behind it in relation to kinetic theory? How do we use kinetic theory to explain Avogadro's law? You have pressure maintained, temperature maintained. So at this point, the number of mole is determined by the number of particles. You know that 1 mole will contain 6 times 6.023 times 10 raised to power 23 particles. It may be atoms, it may be molecules, or thereabouts. Now, so that is the number of moles here. But if you increase the number of moles, you have increased the number of particles, you have increased the frequency of collision, you have reduced the size, the distance between the particles, and because of that, there will be frequency of collision with the wall. And as a result of that, you know that this pressure is maintained constant. It will push that up, and you have an increase in the number, in the volume to correspond to the number of moles that you increase. Another law has to do with mixture of gases, and that is the Dalton's law of partial pressure. The Dalton's law of partial pressure tells us that the total pressure that is exerted by a mixture of gases is equal to the sum of the partial pressure of the component gases. So if you have 4 gases in a mixture, the total pressure that will be exerted by those 4 gases is a sum of the partial pressure of each of the gases that makes up the mixture. That is provided that it's a mixture that is not reacting, provided that there is no reaction between the particles. Then we can combine Charles' law and Boyle's law. When we combine Charles' law and Boyle's law, what we will have is V is directly proportional to T and inversely proportional to P. That means V is equal to K T over P. Then we can say that P V over T is constant. So PV over T is constant. Then the combined gas law of Charles and Boyle's law is P1 V1 over T1. It will be equal to P2 V2 over T2. Now, what this means is that gases will obey both Boyle's and Charles' law and will give you this expression. So you can continue to have that until whatever number of gases that you are considering or number of conditions that you are considering. So you have interactions in, the laws telling you that you can have a combination of the two gas laws. Then we can also have the ideal gas law, that is a combination of the three. The ideal gas law is a combination of B is directly proportional to N and directly proportional to T and inversely proportional to P. Now, the implication is that V then is equal to a constant K, though this constant is actually the ideal gas constant, which is R, N T over P. So we can simply then say that PV, as in this expression, can become PV is equal to N R T. So this is the ideal gas law. This is the ideal gas law that came out of the combination of the Boyle's law. V is inversely proportional to P. Charles' law, V is directly proportional with T. And Avogadro's law, V is directly proportional to N. The constant of proportionality is R, that is called the ideal gas constant. Ideal gas constant, the combination of the three. So we have that expressed here. It's already explained. Boyle's law, Charles' law, Avogadro's law. The three of them to put together, then you have that as your constant. The constant of proportionality is R, and you have the gas constant expressed as that. Now, we can then get a numerical value for that constant. That numerical value for that constant can be obtained at STP. You know that at STP, you have 22.414 liters of as the standard volume. You have 1 atmosphere as the standard number of moles. You have 0 degrees Celsius, which is 273.15 Kelvin as the temperature. And you have 1 atmosphere as your pressure. Putting everything into the equation, you have 1 atmosphere times 22.414 liter over 1 mole times 273.15 Kelvin, and that will give us 0.802057 liter atmosphere per mole per Kelvin. And that is the ideal gas constant in this unit. There is another ideal gas constant in the unit of Pascal or Newton per meter squared. So, gas law problems. There are many variations in gas law problems. So what you have to keep in mind is anytime you are solving gas law problem, you would know that temperature must be in Kelvin, so you convert it to Kelvin by adding 273.15. You can get pressure to be in force per unit per surface area. You can always know that volume of the container will be equal to the volume of the particles or volume of the material you are dealing with. Then you must be conscious of your unit conversion. If you are using mil is the same thing as dm cube. Sorry, liter. If you are using liter is the same thing as dm cube. Mil is the same thing as cm cube. So 1 liter will be 1000 cm cube, which is the same thing as 1 dm cube, and it will be equal to 10 raised to power minus 3 meter cube. So you need to be conscious of your unit in solving gas law problem. So if the problem involves set of initials and final, then you can use the combined gas law. You have the initial parameter, you have the final parameter. If the problem gives you only information of one set of conditions, then you can use the ideal gas law. If you are having only one set, in which case you are not having two sets, initial and final. So then we can also use gas law to determine molar mass of gases. And how do we go about it? You know that density is equal to mass over volume. Density is expressed as mass over volume. And we can substitute for volume from ideal gas law. You know that in ideal gas law, PV is equal to NR Now, if we make V the subject of formula, then we'll have volume to be equal to N over V R C. Now, you know that M over V is the molarity. M over V is the concentration, number of mole over volume. It should be PV, not that's not where I'm supposed to use it. So we are making V the subject of formula, so it should be N over P is equal to this. Now substitute this expression, the whole of this expression, for volume here. Then you will have this expression. If you have M divided by R T times P over N. You know that the number of mole is mass over molar mass. Small n is equal to small m mass over molar mass, capital M, molar mass. Now, if you substitute that here, you will have this expression as equal to mass over molar mass. So this will cancel out that, and this will go up here, and you will have this expression. So which means that if I have the density and I have the pressure, if I have the density and I have the pressure, I have the density, I have the pressure, and I have the temperature, I can calculate my molar mass of the gas. So the molar mass of the gas can be calculated from this expression. Those of you that are already using your hand, you just give me few. Oh, my time is even up. Okay, for the expression I just talked about, in this case, you are given only a single set of units. You are given the mass of your gas, and you are told that it's STP. So you have this as temperature, this as pressure. You can get the number of moles by dividing mass over molar mass to give you the number of moles, and from there you can then get the volume using the expression of V is equal to nRT over P. Then this is another equation. This is another question in which you are also given single units. Single values. You are given double values there. You want to find the pressure, but what you are given, it's difficult for you to. You can't use Boyle's law. You can't use Charles' law. So you'll come up with an expression P1 over T1 is equal to P2 over T2. And how do you get that? You have N, you make nRT over V equal to P over T. So the two of them becomes constant. Then that means that P over T is equal to constant. So nR over V is equal to P over T is equal to constant. So from then, you can then find your unknown. You will have to look at some of these questions. It's in your slides, and the slide is on the LMS. Look at some of these questions and try it on your own. We will conclude the class by looking at other uses of ideal gas law. You can use ideal gas law to get density. You can use ideal gas law to get the molar mass, and you can use it to get the stoichiometry. So these are questions that you are also supposed to try your hands on. They are on your slides, how you can use it to get density and all the other. This is a convenient point for us to stop. I will stop sharing so that I can entertain few questions, not much. So I will unmute you, and you can then ask your question. Let me start with Ayodele Israel that is raising his hand.
Good morning, sir.
Good morning.
Yes, sir. I was lost when you were deriving density from the ideal gas law. When you replaced N over V with the molarity.
N over
V with molarity.
N over V. No.
Yes, sir.
I corrected myself there. N over V is concentration, that's molarity. But okay, it's not that we are making P the subject, V the subject of formula, not P. So that we can substitute for V. So if I may quickly share the screen with you for you to understand what I'm talking about. Coming just
okay, sir.
Give me few. I'll go back to it for us to see what I'm talking about. It's not moving. I may have to exit the screen to get to what I'm talking about. Okay, sorry. I've passed just how to use it to get the city. Okay, if you look at this expression, it is V. It is this V that I wanted to substitute. So I will have to make V the subject of formula from NRT. So in that case, I cannot make P the subject of formula. PV is equal to NRT. So it is V that I will make the subject of formula because it is V that I want to substitute. And that will make V to be NRT over P. So it is this one that I'm going to substitute for V. So this is going to come here, and from there we'll get this expression as I previously explained. I want to believe you can understand what I've explained.
Yes, sir. Thank you, sir.
Any other person, any question? Okay. If there is no question, this is a convenient point for us to stop the class. For those that are not online, they can get the YouTube video very soon. Thank you and God bless.